Hi, this is Dan Bullard, retired electronics engineer, sitting on the fret think of my house plug in. Oh, it's a lovely day. It's the 9th of July. Okay, I'm continuing on with my Nextest DSP training course. I wrote this back in 2003, I think, 2002, 2003. And I was trying to get the Nextest people up to speed on mixed signal. That's been my life's work. Trying to get people up to speed on mixed signal and analog and FFTs and all that stuff. And it's been very rewarding. Okay, so this is part 4. Let's talk about measurement functions. Now again, this is the Nextest software. You may never use it, but it just shows what software should do when you're trying to do mixed signal. So after you capture your waveform, you may want to make a few measurements. Measurement functions come in 4 flavors: time domain measurements, equality domain measurements, like greater than, less than, within bounds, frequency domain measurements, like signal noise ratio, THD, SNDR, and so on, and statistical domain, ILE and DLE, and things like that. Time domain and equality domain measurements will be covered now. Measuring things in time domain. It's cool on a scope, but it's way better on a mixed signal tester if you're coherent. If you're not coherent, there's no guarantees. Now, with a sine wave, and here's a sine wave, you have the average, that's the average voltage, so plus and minus, take the average of the entire waveform, and that's the average. And there's a way to do that. I'll show you a function that does that. You have the positive peak and then peak to peak, and you can also look at the negative peak. It's pretty easy to do. You can do all those things with DSP. You don't have to guess. You may remember the Raytheon guys were trying to measure peak voltage of a very tiny signal, and they basically just took the peak and multiplied by 0.707. That's not a guarantee. If it's not a sine wave, 0.707 times anything else is not the right number for RMS. So the only way to measure RMS is to take the root mean square. Okay, so we start with waveform min-max. A couple of functions here. Waveform min-max, waveform in-wave, double. That's a double precision floating point number. Double min value and double max value. So waveform min max, and you give an in wave, you give a double for the min value, double for the max value, and 2 integers. An integer for the min index and an integer for the max index. That way you can find out where those min and max values were. That could be helpful in some cases. Double waveform RMS. You give it the waveform and it computes the root mean square. That is, it takes the square root of the sum of the squares. It doesn't just multiply it by 0.707. Any idiot can do that. That's not how you get the RMS. The RMS is the root mean square. That's what it means. Now, a real meter that does a real RMS, just use an analog chip, probably an analog devices chip to do it. It's not going to do the real thing. You want to do a real RMS measurement, mathematically compute the root mean square. And to do that, you need to capture coherently. So you capture the sine wave or whatever wave coherently and then do RMS. And so you could even give this a noise waveform and it would give you the RMS value of the noise, whatever the waveform is. If it's a square wave, it'll give you the RMS. There's also waveform standard deviation and waveform variance. I've never used either one of them, but they are there. Here's an example of removing DC offset. So we have a variable we call average. It's just a double. Average equals waveform sum of ACI wave, that's just a waveform, and divided by waveform get size ACI wave. So with these waveforms, you can get all the little internal variables from them by doing waveform get size, waveform get this, waveform get that. Waveform sum of ACI wave divided by get size, so whatever the size is. So it's pretty easy. And then waveform subtract, ACI wave average. So that subtracts out the average value that you measured from the waveform. And so there you go. You now have it basically down at 0. And now you can window it. We talked about windowing in the last one. Never ever window before you do this step. You've got to remove the DC offset. Another way of doing it is to say average equals waveform arithmetic mean, ACI wave, or whatever you want to call it. I'm just using that name. It could be any name. And then waveform subtract ACI wave average. Boom. There you go. It's just getting rid of the DC offset. Easy to do. Now, there are circuits that do that, but you don't need a circuit. You can do it in DSP. That's what DSP is, digital signal processing. Okay, I'm not going to cover all the ED measurements. These functions test the waveform to see if it fits within a value or within another waveform. There are 4 single-ended functions. Less than, so you can say like waveform less than. You can say waveform less than or equal to, waveform greater than, and greater than or equal to. These are the overloaded functions. There's 4 types. Boolean waveform greater than, you give it a waveform and a double scalar. That just says, is this waveform greater than this scalar? It returns a Boolean value. So if it is less than the waveform, then it returns a false. If it comes back true, that means it was greater than the scalar. Waveform greater than waveform in wave 1, waveform in wave 2. That says, is this waveform greater than this other waveform? And so it returns a true if it is greater. Then waveform greater than, waveform out wave, waveform in wave 1, waveform in wave 2. So you can get a waveform that shows you where, if it was greater, where was it greater? So you get a waveform that shows it as a waveform. And then waveform greater than, waveform out wave, waveform in wave, and double scalar. So you compare it against a scalar, so there's a lot of ways to go here. So you can mix and match all these things. All these things I've shown you, you can use them together to do some pretty interesting things. Okay, there's another function, and again, I had to do this for analog devices in Ireland. They asked me the question, and I didn't have an answer right away. They wanted me to help them do it. And I said, you know, you can always just do an FFT. He says, no, this is not doable with an FFT. What we want to do is we want to measure a waveform within a mask. And so they wanted the communications waveform, make sure that the quality of the waveform fit within a mask. And that's waveform within bounds. Now, this is way back in the 1990s. I had to do that myself. And this is now in the 2000s. Daver found a way to do it in the Nextest. And so thank God for Daver. But I did accomplish it. I had to go back to the States and do the work on it. And I made the masks and everything and sent it to them, and they were happy with it. It worked out good for them. So waveform within bounds function, input parameters are overloaded to allow comparison of a waveform thus. Within 2 waveforms, within 2 scalars, less than a scalar or greater than a waveform, greater than a scalar, and less than a waveform. So here's an example of a mask. This is the kind of thing that you would do with analog devices or various other companies, Broadcom. You've got a pulse coming along. You want to make sure that the pulse is high quality, doesn't have too much overshoot, too much undershoot, etc. So what you're going to do is you can validate that the pulse fits within this mask, okay? And you're going to say, whoa, what if it's not properly aligned? Well, you can take care of that. Waveform temp 1, waveform constant fill, object 32 samples 0. waveform temp 2, waveform constant fill, object 32 samples, 1.0. Now we make a pulse. This makes the mask. So waveform copy, temp 1 into object. So temp 1, let's see, that was the 0. So the pulse gets 0, then it gets temp 2 concatenated in. So 32 samples of 0, 32 samples of 1, and then waveform concatenate, object temp 1. So now temp 1 is added on, that's 0, so 0, 1, and 0. Okay, so 32 plus 32 plus 32. And then waveform set X scale, 1 microsecond, and scale seconds. Now, I did want to mention this one thing. These examples, you say, well, again, this stuff looks good, but does it really work? Yes, it works. When I wrote this, not only did I write these examples and compile them, I ran them on the tester to make sure that they did what I thought they would do. Because, you know, it's easy to make a mistake. It's really easy to make a mistake. I spent my life dealing with compiler errors, and you know, even if it compiles, that doesn't mean that it's going to work. So I would write these examples in the code, I would compile them, and then I would try them and make sure that they did what they were supposed to do. So these are all tested that way. Every one of these is a real example, a real working example. Here's another one. Status equals waveform within bounds, tested lower mask, upper mask. So we get a Boolean result called status. We're going to test the waveform tested against lower mask and upper mask. If it doesn't fit, if the waveform does not fit within the mask, if waveform less than tested gross left mask, output the pulse is early. I equals 1 do waveform rotate right. Probably didn't know you could do that. There's all kinds of functions. If it can be done in a CPU, it can be done in DSP. So rotate is one of those things that you do in a CPU. Here I'm doing it to a waveform. Waveform rotate right, tested, temp status equals waveform within bounds, tested, lower mask, upper mask, and increment I. We rotate to the right, so that's this way for me, that way for you. But we're rotating it one step at a time to see if it ever fits. If it doesn't fit, then we're going to jump out. But if it does fit eventually, output pulse was %2D samples early, give it I. So that aligns the waveform for you. So it's pretty cool. Okay, there's no end to the number of things you can do with this stuff. And I've done exactly that with another case. There was a waveform from a free running oscillator, and I had to measure VOL. And you think about free running oscillators, putting out square wave, how do you measure VOL? You can't just stop it, it's running. So what I did was I captured the wave non-coherently, and then I tried to work it out to get it all the samples in the right place, and then rotated around until I got exactly the right set of levels, and then I did a VOL. I took the average of everything that was low, and that was VOL. So I did a VOL test on a free running clock, and that was on an STS 3000. Okay, let's talk about the FFT. The Fourier transform in essence decouple blah 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 blah. This is intimidation. So I'm throwing intimidation at the students and saying, you don't really want to know this shit. That's not what the FFT is about. The FFT is a beautiful and simple thing to understand. Okay. In the early 1960s, Richard Garwin needed Fourier analysis to study solid helium. Think about that, solid helium, that's really something. He enlisted the help of James Tukey, who provided him with the algorithm for the FFT. Then Garwin asked IBM for help in coding the FFT. J.W. Cooley was assigned to work on the problem. the assignment got in the way of his real work, but he did it in his spare time. Now, Cooley was my kind of guy. I mean, Dave and I have done this kind of thing all the time. You're working on stuff because, you don't have anything pressing at the time. So you're working on something, kind of your own little project, and they come along and said, hey, can you do this? And you're like, okay. I was having a good time doing my own little project, but I'll do what I can. So he did it. And he got it done, and he gave it to him, and Garwin says, wow, that's really something, that's really something, that's amazing. And Cooley says, well, if there's anything else I can do, let me know. It was great. So here's a waveform, M cycles long. So we don't talk about samples here, you can, but we see M cycles. How many cycles is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 cycles of the wave. And so if you do an FFT on 9 cycles of the wave, you get the fundamental in bin 9, in bin M. So bin M in the FFT represents the amplitude, the magnitude of the fundamental, and that's the peak voltage. And then bin M times 2 is 2 times the fundamental frequency, 2 times F sub t, so that's the second harmonic. And bin M times 3 is the third harmonic. And we don't have anything else in there. And I made this is real waveforms. What I did is, if you look at that sine wave, that looks like a sine wave, but it's not really a sine wave. I modified it. I added the second and third harmonic. You may not be able to tell, but if you look at it, it's a little bit tilted to one side. That's the second, third harmonic getting in there and messing with the waveform shape. So this waveform actually has second and third order harmonics in it. Doesn't have anything else, just the second. And how do you do that? I've done that in a million different ways. You can do it in a lot of different ways. Okay, going across the waveform, we see there's noise. Okay, way down there, minus 275 dB or lower. So that's way down there, way down there. And then going all the way out to the Nyquist frequency. Never trust the Nyquist frequency. Not unless you're an idiot from MIT and you happen to be running a department. So the fundamental frequency shows up in bin M, that's bin 9. The second harmonic shows up in bin 18, and the third harmonic shows up in bin 27. That's because I use an M of 9. If I use an M of a different number, as long as it's an integer, everything will end up in integer bins. Okay, here's a real nice close-up. So we have the bin M, the harmonics, and the noise. Now here I showed noise, and that's the bin spacing. That's the Fourier frequency. The Fourier frequency is the test frequency divided by M, or the sample frequency divided by N, or 1 over the UTP. That's why I had you calculate the UTP. The UTP determines the Fourier frequency. The longer you sample, the lower your Fourier frequency is. So if you want a really excellent resolution, sample a really long time. Now, you can still take a lot of samples because you can do an FFT and, lickety split, I mean, these days now, FFTs just, they zoom right by. Now, what about this noise? Where is this noise coming from? Look at this, minus 275, probably minus 300 dB. That's kind of where double precision math takes you, to minus 300 dB. So you don't have anything to worry about, but with a real waveform, when you capture a real waveform, you have to worry about the noise that you captured. When you perform an FFT, the noise is spread across N over 2 bins. The larger the value of N, the less noise there is in each bin. That reduces the amount of pollution of bins you care about. The level of noise per bin is reduced by 3 dB for each doubling of N. That is 20 times the log base 10 of 1 over the square root of 2. So if you double N, you reduce the noise in each bin by 3 dB. Making N very large brings the noise floor down below the very low level signals. Now, in Matt Mahoney's book, I'm going to say this, Matt Mahoney was a genius, but Matt Mahoney was wrong. Matt Mahoney did an example in his book. If M is not mutually prime with N, then you get funny little things popping up in the spectrum. What he didn't know was those things are real. If M and N are not mutually prime, and I forget the example, I mean, I don't have my book anymore, but if M and N are not mutually prime, what's going to happen is the noise is going to go down. You're basically averaging. You're averaging. The noise level goes down, and the harmonics and other things start popping up. And so what he didn't realize was that by making M and N not mutually prime, the noise was going down and the signals like harmonics and other things were coming up. So if you want to see really tiny things, you have to make N really large, really large. The larger you make N, the better, because every time you double the number of samples, N, the noise floor goes down by 3 dB. Now that's one of the beauties of the sigma delta converter. One of the problems with the early sigma delta converters, they put them into CD players. And so the Radio Shack guys, the guys who sold electronics, were told that the more bits that a CD player had, the better the sound quality. So here's a 12-bit CD player. It sounds like this. Oh, that's pretty good. And then a 14-bit. Oh, that sounds even better. And then a 16-bit. Oh, that sounds even better. And then they came along with the 1-bit sigma delta converter. And what are the salesmen going to say now? Well, I can't sell a 1-bit sigma delta converter. I've been telling my customers that the more bits, the better. So now, if the customers are going to come in and they're going to say, I bought that 16-bit CD player from you, but I want to know if they got a 24-bit or a 20-bit yet. No, no, no. We went to 1-bit. 1-bit. So why does the sigma delta converter work? Why is everything now sigma delta? Because they oversample. They sample really, really fast, and so they take a lot of samples. And so a sigma delta converter samples very, very fast, but even though it's 1 bit, it sounds better than a 16-bit A to D or D to A. So that was a quandary that the poor salesmen at Radio Shack and all these other electronics places had, because they had sold all these CD players saying, oh, the more bits the better, and now suddenly you got to say 1 bit's the best. Oh my God, how do you deal with that? It's pretty obvious you've been lying the whole time. Okay, so the more samples you take, the lower the noise floor goes. That is, if N goes up, the noise floor goes down by 3 dB. Every doubling of N is 3 dB. And because computers have gotten so fast now, you can do an FFT in no time. So you can do an FFT of more and more and more samples very, very fast. Back in the old days, when I was working on this stuff back in the 1990s, computers were so slow, it would take forever to run this stuff. Now, boom, gone in no time. I mean, we were doing, even in the 2000s, we were doing FFTs in 1 millisecond for 2048 point FFT. 2048 point FFT in a millisecond. So nowadays it's probably in the microseconds. So we're gonna do 1 or 2 more episodes, so watch for those. But until then, this is Dan Bullard from the river. See ya.